Hi everyone. I've got a nice problem for you guys that I thought about the other day, and it touches on several techniques in probability theory and some things regarding sequences and how to manipulate this in general to try to get some standard computations that you might have learned in the first class in probability, but it's not as straightforward. So we'll consider a random variable x from a geometric distribution. And the geometric distribution in this case is starting from 0 rather than 1. So its probability mass function, PMF, the probability that x equals this certain integer, is given by 1 minus p times p to the kth. Now this random variable x in itself is not my random variable of interest. I'm actually interested in if I were to sample this random variable and then take that as my index for the term in the Fibonacci sequence, what that resulting value is my interested random variable. So my interested random variable is y, defined as the xth term in the Fibonacci sequence. So x here being the random thing, in the Fibonacci sequence being this very famous, well-defined sequence with the 0th term being 0, the first term being 1, and terms henceforth being the sum of the previous two terms. So just to give you an idea how this looks, we have this following table. So x being 0, 1, 2, 3, 4, 5, let's say. Then the resulting values of y would be 0, 1, 0 plus 1 being 1, 1 plus 1 equaling 2, 1 plus 2 equaling 3, and 2 plus 3 equaling 5. And this goes on forever. And the resulting probabilities would be, the probabilities would be 1 minus p times nothing, 1 minus p times p, 1 minus p times p squared, 1 minus p times p cubed, 1 minus p times p to the 4th, 1 minus p times p to the 5th, and so on. And then the properties I'm trying to correspond to are between y and this probability, not x in the probability. And we're going to use this to now to find common functionals, common characteristics, such as the expected value of this geometric distribution on the Fibonacci sequence, if you will, the variance of this random variable, and then what's the probability that this random variable will be even. So let's do that. So I wonder if it would be interesting if I just put this little table right here for now. Cool. So for problem A, not number A, we have the expected value of y. When written out, it's going to be literally k equaling to 0 to infinity of a of k times each of these resulting probabilities, 1 minus p times p to the kth. Now, the Fibonacci sequence is a very famous sequence, and you can look online that there is a closed form for the Fibonacci sequence, but let's not use that. Actually, I don't even think it would be helpful, to be honest. The most helpful thing is actually its defining relationship, which is from this recursion. But at first, it doesn't seem really computable what this expected value is, right? In fact, if you do look up the exact form for the Fibonacci sequence, you get something along the lines of a of k equaling to the golden ratio, phi, to the kth power, minus the negative of the golden ratio, 1 over the golden ratio, I guess, to the kth power, divided by square root of 5. Now, this, when plugged in, doesn't really, it does help. You can do this directly, But the way I want to approach this is actually to use the definition of the Fibonacci sequence to give me some kind of functional relationship that involves expected value of y on both sides of the equation and solve for that. That's the more beautiful way, in my opinion. Also teaches you something about generating functions, for those of you familiar with that. There's actually a very clear relationship between the expected value and the generating function for a Fibonacci sequence. But we'll take this to be a self-contained problem and not worry about this and just show how to solve it directly. So taking this defining equation for the Fibonacci sequence, I'm going to multiply both sides of this by one minus p times p to the kth. Nothing's changed. And it certainly remains true if I then sum both sides from k equaling to 0 to infinity. Right? So how does this help us? Well, analyzing this term right here, this is exactly the expected value of y. So I can just write this here. But what are these two things right here? We're off by an index of +1 and +2 on these expressions. So what can we do to then try to make the index match up in some sense to give me something that's in terms of expected value of y? Well, since this p of k is one lower than this k plus 1 in terms of index, you might imagine that if we take this expected value of y right here and then divide it by p, that it'll give us the exact index. Let's see what happens. So the expected value of y given divided by p would then be summation of k equals 0 to infinity of a of k times 1 minus p times p of k minus 1, okay? Because we've divided by p. So we've reduced this p of k to k minus 1. Now, when we reindex this, we have to realize that, well, let's think about this. When k equals 0, we have a 1 minus p times p to negative 1 power out here. That's something we don't want, right? But a of k of a of 0 just equals 0. So that term just disappears. So we don't have to care about that. So it actually turns out that this actually just equals the same thing once we perform a reindexing, that k equaling to 0 to infinity, and then we bump this k to k plus 1, 1 minus p, and then we bump this k to k plus 1, but then we minus 1, which gives us just a to the k. So it turns out that exactly e of y divided by p gives us exactly this term right here. Right? Now let's do a similar trick for this term right here and see what happens. So we'll remove all of this. And to try to get this k plus 2 and this p of k, this offset term, let's consider this expected value of y divided by p squared. So upon doing that, we get summation of k equals to 0 to infinity of a of k times 1 minus p to the p of k minus 2. Now, when k equals 0, a of 0 equals 0, so that term goes away. When k equals 1, well, that equals 1, so that 1 minus p term doesn't go away, right? So that's a bit annoying. But then we realize something that's kind of nice. So we then just simply subtract that term in the initial expression. So if I do this minus what a of 1 times 1 minus p to that power is, that term that I'm missing is here. So it turns out that exactly this is as if we started from k equals to 2. And then upon another reindexing right here, we have a of k plus 2 times 1 minus p times p of k. Great. So that means we can then write this term right here as such. And now notice that with this kind of clever rearranging, we have expected value of y on both sides of the equation, and then we can solve for it in terms of p. And upon solving it, we get that expected value of y equals p times 1 minus p divided by 1 minus p squared. And that's our expected value. Notice that the expected value is only finite for certain values of p. I'll leave it to you to check that this is only finite. Exists only for p in interval 0 to square root of 5 minus 1 divided by 2. And that's because the smaller root of this equation right here is square root of 5 minus 1 divided by 2, the silver ratio, if you will. And then it dips to be a negative. So that concludes part A. So let's do part B. I'll leave this here for now, as you'll see. So for part B, we'll use blue. I want to compute the variance of y, which we know to be the expected value of y squared minus the expected value of y entire quantity squared. So if we write this out, we know what this is already from here. So we plug this in right there. So now what we're left with is this thing. So writing out the expected value of y squared, this would literally be the k equals to 0 to infinity of a of k squared, 1 minus p times p to the kth power. Now, the trick we've done before, using the Fibonacci sequence to give us a defining equation which we can then solve for y, can be applied here again, but we need a trick. Because our recurrence relationship here is not in terms, it's a linear in terms of these previous terms, but we have a squared here. So, okay, let's see what happens if we square the Fibonacci sequence as a first run, right? So we have a of k1 squared plus a of k squared plus 2a of k plus 1a of k. So we could try to set up a recurrence relation defining equation from these two things here. But the problem is we have this cross term right here. And this cross term can't be easily related to these existing terms. So we need something different to then kind of cancel out those cross terms. So how do we do that? Well, it turns out that we can do this. So consider a of k plus 3 squared plus a of k squared. A of k plus 3 squared is just a of k plus 2 plus a of k plus 1 entire quantity squared. And then a of k looks something similar, except we're going to have a minus here. Why? Well, a of k plus 2 equals a of k plus 1 plus a of k. So if I subtract a of k plus 1 from both sides, I get a of k, and then I have a of k plus 2 minus that, a of k plus 1. And the reason I'm doing this is because you can see that these two things look almost similar, except one's a plus, one's a minus. But upon squaring both of these quantities, the cross terms are going to be of opposite parity, one of positive, one of negative. So they're canceled out. So this gives me something that looks like 2 of a of k plus 2 squared plus 2 of a of k plus 1 squared. And I don't have any pesky cross terms here. Sure, I get an additional 2 term right here, but that's not going to affect anything because I can just bring that 2 out when I come up with my defining equation. So let's do that same trick again. I'm going to multiply both sides by 1 minus p times p to the kth, and then take the sum over that. Oops, sorry. I know I'm a bit quiet right now, but I just want to write everything out. Okay? And now we're going to do the same trick of trying to match terms to things that will be a function of the expected value of y squared. So this term right here is exactly expected value of y squared. Now I'll leave it to check to you that the remaining expressions can be expressed as follows. So basically the idea is, once again, when we divide by some kind of p to the kth power to try to reduce the index to match between this offset term, here being 3, for example, we then have to subtract off the first 3 terms of the Taylor series polynomial so that we don't have that kind of negative indexing going on. And it turns out those 3 indices are corresponding to this quantity being offset by 3 will be a 0 minus p times 1 minus p, and then minus p squared times 1 minus p. So upon solving this entire expression, we do get the expected value of y squared to equal, let me just check my notes to make sure. We'll get this to equal 1 minus p squared times p divided by 1 minus 2p minus 2p squared plus p cubed. So taking this expression right here, and plugging it back here, and then subtracting off the expected value of y quantity squared, we get our result. Pretty neat, would you say? So let's erase this and move on to the third problem. So now the third problem is asking, what's the probability that our random variable, the geometric distribution of the Fibonacci sequence, is even? So to get intuition of that, let's write some terms out. So we have a of 0 equaling 0, a of 1 equaling 1, a of 2 equaling 1, a of 3 equaling 2, a of 4 equaling 3, a of 5 equaling 5, a of 6 equaling 8, 7 equaling 13, a of 8 equaling 21. So notice that there's a pattern. In which case, all the even terms of the Fibonacci sequence correspond to every third multiple of the index. And all the odd terms of the Fibonacci sequence are just the non-multiple thirds of the sequence. So which is to say that y is congruent to 0 mod 2 if and only if x is congruent to 0 mod 3. So finding the probability that y is even is equal to finding the probability that x is a multiple of 3 among the natural numbers starting from 0. So this would be the sum of the probabilities, with k now just taking on multiples of 3. So notice that this is still a geometric sum with initial term 1 minus p because we're starting from k equaling 0. But now the ratio between each term in this geometric series is p cubed. So using the geometric series formula, this would be 1 minus p over 1 minus p cubed. And this denominator right here, 1 minus p cubed, can be factored into 1 minus p, parentheses, times 1 plus p squared. So that cancels out with a 1 minus p in the numerator, which then gives us 1 over 1 plus p squared. So that's the conclusion of all these three parts to this problem. And thank you for watching.